Now this is a very similar application. You might think, why bother with another one? But because it's a temperature function in x, y, z. This isn't an ant on a two-dimensional surface walking around. This is a bird flying in three-dimensional space, which of course is a much better application of temperature functions for things that we humans have to live with, right? Okay, so we have this temperature function. We have the bird at that point. So there's the point P, -2, 4, 2. So the first thing we want to know is, what is the current temperature? Well, again, that's quite easy. We would just take our temperature function and we would stick the values -2, 4, and 2 into them. Substitute 50 over the square root 1 plus -2 squared plus 4 squared plus 2 squared. All right, so that's 16, 20, 24, 25. So this is the square root of 25, which is 5, which is 10 degrees. I assume this is Celsius again. There we go. Done. Easy. All right, what about B though? Well, we need a direction, so we need to unitize the direction vector. And then we also need to find the gradient. So let's start with the direction vector because that's actually easier. The direction vector, and I'm going to number it number 1 because I can see there's a second direction vector coming. So that will be 3, 1, -1 divided by the square root of 3 squared plus 1 squared plus -1 squared. All right, so that would be 9 plus 1 plus 1 is 11. So this is 3 over the square root of 11, 1 over the square root of 11, -1 over the square root of 11. Done. Direction vector found. No problem. Okay, what about our gradient? Well, that's going to be a bit trickier. For starters, I want to think about rewriting this. This is equal to, I'm just going to write it up here, 50 times 1 plus, I'm going to have to make my page number disappear so I have room to write it. I should have written higher, I guess. 1 plus x squared plus y squared plus z squared to the -1/2. So the 1/2 power makes the square root, and the negative means it's in the denominator. Okay, so that'll be easier for taking the derivative of it. So the gradient of t is equal to t sub x, t sub y, t sub z. Oh boy. Okay, so this is going to be tricky to fit at all in here. I think I'm not going to be able to. Okay, so if I bring the -1/2 down, -1/2 times 50 is -25. So I'm just going to do that right now. -25 times 1 plus x squared plus y squared plus z squared to the -3/2 power, because we subtract 1, times the derivative of the interior with respect to x, which would be 2x. And then the other ones will work the exact same way. -25, 1 plus x squared plus y squared plus z squared to the -3/2 times 2y, and then -25, 1 plus x squared plus y squared plus z squared to the -3/2 times 2z, close my bracket. Ugh. All right, well, that's pretty awful. So, but we can make this a little bit easier. So it's really 25 times 2 is 50. So it's really -50 over 1 plus x squared plus y squared plus z squared, -50x, excuse me, to the 3/2. And then the same thing again, but with y. And then the same thing again, but with z. Okay, so that finishes that. Now, it's ugly, and I have no desire to do a dot product with this. But I don't have to. I want it at the particular point that I'm looking at. I want it at, I want the gradient at the spot that I'm looking at. So the gradient of t at point -2, 4, 2, because that was the point we were given. Okay, So for that, I'm going to start substituting in values. So, and actually, let's just do ourselves a favor real quick. Um, let's just take an aside here. Note, okay, 1 plus negative 2 squared plus 4 squared plus 2 squared to the 3 halves. I think we can find this. This is 4 and 4, so that's 8. 8 and 16, that's 25, right? And then the square root of 25 is 5, and 5 to the third is 125. So this is 125. There, just to confirm myself. I just did it in Desmos. I can do it in Maple, of course, as well. So there we have it. So I'm indeed right. It is 125. Well, that's going to make things a lot nicer here, because then I know that my gradient is negative 50 times negative 2, right, which is 100 over 125. Negative 50 times 4 is 200, so negative 200 over 125. And then negative 50 times 2, so that's negative 100 over 125. And all of those reduce down. So that would be 4/5, negative 8/5, and negative 4/5. Lovely. Okay, so now for our directional derivative, this is in direction u1 of temperature function t at the point negative 2, 4, 2. Because, of course, there's lots of different ways we can go. That would be the dot product of 4/5, negative 8/5, negative 4/5 with 3 over the square root of 11, 1 over the square root of 11, negative 1 over the square root of 11. And then this is all over 5 square root of 11. That'll be 12, take away 8, plus 4. So I can actually do this one in my head. So it's 12, take away 8 plus 4, all over 5 square root of 11, which is 8 over 5 square root of 11. And of course, we can come up with a decimal approximation for that. Just in case we're curious to know the magnitude of it. So it's about 0.482. And keep in mind, that would be degrees Celsius per meter, right? So degrees Celsius per meter, if we're assuming the same units as the previous problem. Sorry, I shouldn't have circled that. Right, same unit for both of them. All right, now what about C? If the bird flies in the direction negative 3, 0, negative 4, find the rate of change of temperature. Okay, so it's pretty simple because we already did the hardest part. The gradient is the hardest part, this guy right here. So this little bit right here is the trickiest bit. But we have it, and it's still the same for this portion. We just have to go a different direction now. So for C, we just need to find that new direction. So U2 would be equal to negative 3, 0, negative 4, divided by the square root of 3 squared plus 4 squared, right? Because the 0 squared doesn't do anything, which is the square root of 25, so that's 5. So that's negative 3/5, 0, negative 4/5. So the directional derivative, but in this time it'll be the direction u2, not u1, of the temperature function at the point negative 2, 4, 2. So it's not just generic, it's not all of them, it's just the ones we found, right? Because we're using these particular values at this particular point. So negative 8/4, negative 8/5, negative 4/5, dot product with our new direction vector, which is negative 3/5, 0, negative 4/5. And again, this is really easy. The middle term is going to become 0. That's negative 12/5 plus a 16/5. which is 4/5 or 0.8 degrees centimeter per meter. I'll just leave it like that. Now you'll notice in both cases it's warming, right? Because of the direction this bird is heading, it's warming in both cases because they're both positive. But it's a bird moving in 3 dimensions, not an ant moving in 2 dimensions like the previous problem.